So let's recall, we had a graph complex. An n-marked version of Konsevich's graph complex. Denoted G upper Gn for integer parameters G and N. This is at least when 2G minus 2 plus N is positive. And let me remind you that this is a rational chain complex of finite dimension. Its differential I will put aside for the moment because we'll be interested in its Euler characteristic. And in degree P, it has a basis consisting of connected, stable, marked graphs. So G a graph together with M a marking. Without loops, which have only alternating automorphisms. And exactly P+1 edges. Remember, alternating automorphism means that the automorphism group of the combinatorial data GM acts only via alternating permutations on the set of the P+1 edges. So in other words, aught GM acting on the edge set EG factors through the alternating subgroup. That's what alternating means. Is it okay? So if you did the problem set, then you saw the following. So let me see if, yes, okay. So here's our example of the graph complex G14. I haven't written in the differential, but if you did the problem set, then you would have encountered this graph complex as an example. Here you see that it has degree, it has dimension 9 in degree 3 and dimension 6 in degree 2. And here what I've drawn is the marked graphs G comma M of genus G with 4 marked points with 4 and 3 edges respectively. And I claim there are no others. And these are exactly the ones with alternating automorphisms. In fact, I think mostly, yeah, they have trivial automorphisms in this case. And what I haven't written down is an arbitrary ordering on the edge set. So remember that the generators were subject to relations depending on a particular ordering of the edges of the graph. Equivalently, you can think of it as an orientation of the real vector space with basis equal to the edge set. Is it okay? This is a review. And so what we're interested in is so let's fix G. I'll fix G at least 2. And let Z sub G denote the Frobenius characteristic in the sense we defined last time. Of the sequence of SN equivariant Euler characteristics of the graph complexes GGN. So that is to say, we consider Wn the alternating sum over all homological degrees P of GGNP. So I write brackets here, again, to indicate that the element in the Grothendieck group of SN representations. But if you want, you can just think of this as a number. Namely, this is the Euler characteristic of the graph complex, the alternating sum of the dimensions of the graded pieces. But since we have an SN action in hand, it's best to sort of remember that structure and study it. So this is Wn, a virtual SN representation. And then the main theorem is about ZG. Let's see. Let me state the main theorem. And this is the main theorem of this pair of lectures, joint with Faber, Iglesias, and Payne. And actually, it's such a pain to write out that instead of taking about 10% of my talk just to write the theorem, let me share my, oh, I can't share my screen, hold on. Let me share it on my other device if I can. Sorry, give me a sec. Yeah, so here is the statement of the main theorem, which hopefully you can see. Let me know if there are any technological issues. So here's the main theorem. It's a statement of Z sub G, so the Frobenius characteristic of the Euler characteristics of the graph complexes. So again, this is, you fix a single genus G and you let n vary. Okay, should I make some remarks? This is quite a formula, right? You can see that there's a lot of, there's a lot going on. There's a certain sum. It's not even clear that the sum is finite, but this is the case. There's a B sub R, that's a Bernoulli number. There's this factor, which maybe I'll have time to, convince you of a shadow of why this factor should be there if we get to it. This whole thing is supposed to be an element of the ring lambda hat of completed symmetric functions.
You really have a question, which you may want to wait till you finish this bit to say, is there a nice form involving plethisms?
Is there a nice form involving plethisms? The formula does not involve plethisms. I'm not sure why it should. You often, okay, so this is getting a bit ahead. Sorry, Diane, was that your question or was that from the chat?
This was from the chat.
Ah, sorry, okay. I can't see when I'm sharing the screen. Yeah, so yeah, this is getting a bit ahead of myself. One can sometimes use plethisms to encode certain sort of like grafting operations on graphs. We won't need that particular kind of thing here, but you can see similar formulas involving plethisms. I completely agree in other contexts. Here we won't need that. A very, very rough avatar of why that would be the case is that we have a certain contractibility result in joint work with Iglesias and Payne that allows us to, usually when you have these kinds of formulas, you have to be able to graft lots of trees of marked points onto fixed genus D graphs. But in this case, we know that non-trivial trees of marked points contribute trivially to the Euler characteristic. This is not at all obvious. So yeah, no, I don't need plethisms in this formula. However, it might not be completely visible that this thing is a symmetric function, or a completed symmetric function. And it is, that's due to these capital P here, the capital P's here. So the capital P's, recall, are inhomogeneous power sum symmetric functions and interpreted in the ring of the completed ring of symmetric functions. This is the Frobenius characteristic, Z sub G. Okay, good. Any other questions? And let me know if I answered your question regarding plethisms appropriately. Great, okay. Oh, what is mu? Yeah, so mu is, it's 0 if the number has a, sorry, so 0 if the number, if the given natural number has a square factor, a square prime factor, and if the number is square free, then it's -1 to the number of prime factors. So it's the number theoretic mu. Is that okay? Great. Okay. Oh, thank you. Great. Yeah, it's that mu. It's the one you might have seen in elementary number theory. Okay. Let me let's see. Let me share with you a different thing. Okay. So let me give you some historical context for this formula. So this is the formula. You can see, so the top line is Z2, the second line is Z3, and so on. It's quite remarkable. I produced this PDF just by programming my computer using the previous formula to just output the explicit expressions. So there's a lot to say regarding the context of this formula. It was conjectured by Zagier in 2009 following Faber producing and proving this formula to, or proving the formulas you see in this screenshot to hold for G up to 8 and subsequently 9. And what Zagier did was, so Faber showed this data to Zagier, so you can imagine just seeing the first, all but the last line of data. And Zagier conjectured the previous formula that I just put up based on that data. This is quite remarkable, I think, to say the least. So this formula proves Zagier's conjecture from about 2008. There hadn't been really progress on this this conjecture until this tropical approach, which we came upon quite recently. So I'm excited to share it with you. Okay.
So can I check? So these are rational functions, or they are polynomials? Is the whole point after at the end?
Yeah. Okay. Let me. Sorry, I'm in a bit of an awkward technological zone because let me go back to my my own whiteboard. Oops. Yeah. So this formula involves. Okay. So we showed the theorem. So the remark is that, let's recall, the inhomogeneous power sum symmetric function. So P sub k is 1 plus little pk, where little pk is the sum of the kth powers of all the variables. So here, what do we interpret? So you saw that the formula was in the format of a finite sum of Laurent monomials in, let me just write this instead of gesturing at it. So let's remark that this formula is a finite sum. It's a Laurent polynomial. That's what that's called. Sorry. So Laurent polynomial in the inhomogeneous power sum symmetric functions, pi, homogeneous of degree 1 minus g. So in particular, there are like pi's in the denominator, and those should be interpreted the way you expect. So if you have a 1 over 1, sorry, if you have a 1 over capital pi, that's a 1 over 1 plus little pi. So this should be interpreted as a 1 minus pi plus pi squared, and so on. So in this way, this thing, when expanded out, really is an element of lambda hat, because it's like some, you know, power series in the little pi's. Did that answer your comment?
Yes, thank you.
Okay, great. Okay, so that's the, so I did some of the contextual remarks. Another remark is that this should be compared to a similar formula obtained in earlier work of Gorski. Sorry, I don't remember the year on this, but it's in this, you know, in this century. So this is a formula by Gorski on the SN equivariant Euler characteristic of MGN. And the formula obtained by Gorski is quite a similar flavor. It is a Laurent polynomial, again, in the inhomogeneous power sum symmetric functions, which, regarded as such, is homogeneous of degree 2 minus 2g. And this is, I mean, I don't know what to say. There's a lot that this hints at. You know, you often encounter sort of half dimensionality in tropical geometry. And indeed, some of the proof of our formula was inspired by Gorski's techniques, where we're placing algebraic curves in his arguments. One replaces algebraic curves on the side of Gorski's paper with graphs coming from tropical geometry. Finally, I should remark, in case you're not carefully following Stagosaur, that our formula is also the Frobenius characteristic of, so it's also the Frobenius characteristic of the top weight Euler characteristics. Let me just write it like this. So the sequence of Sn representations Wn prime, where Wn prime is the top weight Euler characteristic of MGN, of that same moduli space. So, and this isn't orbifold Euler characteristic in the sense of Harazagier as presented in Stagasaur. This is literal Euler characteristic as a topological space, you know, the coarse moduli space, MGN, if you wish. By the identification theorems that you may have studied in the Stagasaur seminar. So again, by identifying graph complexes as quasi-isomorphic to cellular complexes, cellular chain complexes of the tropical moduli space, and then identifying the tropical moduli space as the boundary complex of a particular compactification of MGN. So this was really the context in which Faber had his original data and theorems for Z sub G for G up to 9, and in which Zagier made the conjecture. And a final remark is that there's closely related work by Topmene Turchin, who, unpacking things, have a different formula for Z sub G, an entirely different formula for Z sub G. And they are studying graph complexes in, seemingly, at least to me, with entirely different motivations coming from the topology of string links. And it's quite unclear, at least at the moment, how to even relate the two formulas and compare them. Okay, so those are hopefully some helpful contextual remarks and some of the history. So let me ask if there are any questions. Yeah, let me ask if there are any questions. And I'd be delighted to answer questions, or at least try. They help me stay on task. So while you think of any questions, let me tell you my plan. So my plan is to sort of let everyone sit back a little bit, and I'll wave my hands at some aspect of the proof. It's a fairly involved combinatorial proof, and I don't expect to go through every detail, but I'd like to at least give you a faint whiff of some of the constructions and some of the reductions that come together in our proof. And then, so for that part, you can kind of sit back and just try to get the gist of it. I mean, you're welcome to hold me to details as well, but I might punt. And then at the end of the talk, I will leave myself time to talk more precisely in a way that, you know, is like sort of rigorous about orbifold counting and groupoid cardinalities. And that will be on the homework. So that's the plan for the rest of the time. I see there's a question. How does, okay. So the question is, how does Gorski's formula relate to Wn prime? So it's not, so Gorski, quite simply, Gorski calculates the entire Euler characteristic of MGN as a virtual Sn representation. We are calculating the top weight Sn equivariant Euler characteristic of MGN. So in other words, with respect to the weight filtration, some portion of the cohomology of MGN is following into top weight, and that's the Euler characteristic that we're calculating here. So that is, yeah, so this remark about Gorski's formula, I mean, it's thematically different from the first and the third remark. So we here are calculating combinatorially the Euler characteristics of graph complexes, but by the comparison theorems that you may have seen in the past 7 weeks, we're also calculating the top weight Euler characteristic of MGN. Yeah, okay, great. Thanks for the question. Any other comments? Okay, so you ready to prove the formula? It's can't prove the whole thing. Let me try to give you a sense. I really will try to give you a sense for at least some of the aspects of this formula. So if you were diligently doing the homeworks, then you will recall the definition of Frobenius characteristic, but just in case, let me write it down as follows. So remember, this Frobenius characteristic knows all the Wn's at once as Sn representations. And of course, to know an Sn representation is exactly to know its character. And the packaging of the Frobenius characteristic is as follows. So this Z sub G is a sum over all n's, all permutations sigma and Sn, and all, all homological degrees I of this expression. So here, this is the character of the Sn representation GGN sub I at the permutation sigma. And this character, it's like, it's a number, and that number is acting as the coefficient of this psi of sigma, which let me remind you, this is a symmetric function. This is, you can write it P sub A1 through the product of P sub A1 through P sub AS, say, where the permutation sigma has cycle type. Can be written as a disjoint union of cycles of length A1 through AS. And again, these little p's are the power sum symmetric functions. Okay, so that is that okay? That's the Frobenius characteristic. So again, it just knows all the characters and hence the representations. So what does this mean? Okay, so what is a trace? Sorry, what is a character? The character is a trace, right, of a certain matrix. So if you write GGN sub I in terms of a basis, if you write the action of sigma on the vector space GGN sub I in terms of a basis, you get some square matrix, and the character is the trace of that matrix. And we have a basis that we in fact described on the first slide. It's the basis of alternating connected stable graphs of type Gn with exactly I+1 edges. So we just have to calculate traces, which means the following in terms of combinatorics. And here I'm going to start being a little fast and loose, but feel free to just push back in the chat if you want more details, and I'll do my best. So if we are to compute these traces, our goal is essentially reduced to a counting problem. Our counting problem is as follows. We want to count. Let me write this as problem number 1 because we'll go through a series of problems. We're going to count marked graphs, so pairs GM, that are fixed by a given sigma. So for every sigma, we want to know how many marked graphs GM are fixed by sigma. Again, that's because you imagine looking at the matrix expressing how sigma transforms the vector space GGNI, and you want to know what are the entries on the diagonal, which again corresponds to fixed points under this action. And this count has to be weighed as follows. So this should be a weighted count. And the count is as follows. If G is alternating, so if G comma M is alternating, then remember this thing actually appears in our graph complex. And because we're doing an Euler characteristic, it should be counted according to the parity of the number of edges. So it should be counted with coefficient -1 to the number of edges if G comma M is alternating. And if G is not alternating, then it doesn't appear, as you remember, zeroed out by the relations in our graph complex. So it should be counted 0 times. Is it okay so far? Because this is, at this point, we just go into combinatorics. Not just, but we do go into combinatorics. And the combinatorics is quite fun. Is this okay? So just because I don't want to lose anyone at this point, it's somewhere here, there's, maybe just writing a little example inspired by the second slide. This G sub I upper Gn has a basis consisting of G comma M that are alternating. And we're interested in summing up the diagonals of the matrix that expresses how sigma acts on that graph, on that vector space. And that means that for each of these graphs, we want to know if it is fixed by a given sigma, then either it appears with, yeah, so then we want to know, you know, does it appear, what coefficient does it appear with, and does it appear at all? Okay. Okay, great. Oh, sorry, and the coefficient is actually, I should put in the symmetric function here. Okay. Great. Oh yeah, you know, I feel like I'm missing, okay, so this is a plus or minus. I'm sorry about this. I'm already becoming a little bit fast and loose with signs. The reason is that sigma might take the ordering, the total ordering of the edges of G to ordering that differs from the original one by a non-alternating permutation. So I think throughout, I'm just not going to worry about signs and be quite informal about that. Okay. Is that plus or minus the sine of sigma? Okay, so no, yeah. So sorry, I think I screwed this up in the notes. So I'm trying to see if I can get it right on the spot. I think what it is that if, okay, so let me just write the sine. And I think what it is this sine is as follows. You see, suppose that sigma acts on, okay, so suppose sigma is acting on the pair G comma M. It acts by permuting marked points, right? So that action is exactly by composing, so first do sigma and then M, I think, right? So I'm saying, suppose that GM is actually fixed by sigma. What do I mean by that? I mean that this resulting graph is isomorphic to G comma M. But that isomorphism can be achieved either by an isomorphism that is an alternating permutation on the edge set or a non-alternating permutation. Does that make sense? So this isomorphism, let me call it phi, is induces a permutation. Let me just write phi restricted to the edge set on the edge set, and that permutation is a sine. Okay, I hope this makes sense. Actually, this might be. I'm probably going to be sad about.
You clearly have some people with you, but I'm
Yeah.
I'm a bit lost. Can you give us?
Yeah.
Can you just?
I was just about to say.
I think the formula was way too fast for me. So I'm spending time looking back over what other things are. Can you just talk through the pieces of the formula at the top?
Yes. Okay. The formula at the top. Okay.
Then you can ignore me after that and continue where you were.
No, I'm happy to. I have a sort of to-do list here. I wanted to explain this sine computation since there was a question about that. Let me go back to the formula. Okay. So first, let's fix an n, like 5 or something. Then you just look at look at this formula for n equals 5. It's a sum over all permutations in S5 of these characters, right? This is a way of encoding exactly the Euler characteristic of the graph of the chain complex G upper G5 as an SN, as a virtual SN representation. Why is that? Because you're just hanging these numbers, these chi's, these traces, on the clothesline that is the power sum, the product of the power sum symmetric functions. Like remember that the power sum symmetric functions P sub lambda, as lambda ranges over all partitions of n, constitute a rational basis for the degree n homogeneous symmetric functions, right? So if I want to remember a bunch of numbers, one for each lambda, then I can just hang them as coefficients of the corresponding P sub lambdas. So you see here that for a fixed n, this formula just tells you exactly what these chi's are, the Euler characteristic of the virtual SN representation, GGN. Is that okay, Diane, specifically?
Yes.
To have you. Okay, and then you just sum over all n, and that's the Frobenius characteristic. Okay.
So why is that am I missing, why is that a finite? Oh.
I'm specifically not clear. It's an element of the completed ring of symmetric functions.
No, I think I'm stuck on the p's live where. That's sorry, sigma has size what?
Sigma is
sigma's in SN. Sorry, I see. So that's why it's okay.
That's right. Yeah, they're exactly n factorial of these. Yeah. I mean, look, like the p's, I agree, they're infinite, they're power series and infinitely many variables. But nevertheless, the ring of symmetric functions is finite dimensional in each degree. Okay. So now let me continue to answer Vance's question, even though Vance is apparently already happy. Let me give you an even more slower example of this calculation. So let's zoom in and suppose that we're interested in the permutation. So example continued, or maybe an example of the example. So suppose we have the following permutation written in cycle notation. This is an element of S6. And I am interested in the following genus 2 6-marked graph, like this. So this is indeed an alternating marked graph. And so it appears somewhere in my, basis for, this is a basis element of the basis I chose I guess, G2, 6.
So we have another question here about where is the alternating sum?
Okay, let me finish my sentence and then I'll get to the question. So the end of my sentence is as follows. So you have some matrix encoding the action of sigma. And somewhere there's a column and a row corresponding to this basis vector. So look, so sigma applied to this thing just permutes the points according to the permutation, right? So it's this graph with 4, 5, 6 on the top, 1, 2, 3 on the bottom. And now the crucial point is that the marked graph you started with the given edge ordering is related to the marked graph you ended with the same edge ordering according to some permutation of edges, right? This isomorphism, let's see, I think it exchanges 1, 2, 3, 4 pairs of edges in this cases. So you would have a +1 here. That's the sign that I should have put in before. Okay, so I hope that the gist of the idea is evident. Okay, question. You're thinking of it as a cycle index. Can I recall why we are having an alternating sign? The alternating sign is because I am calculating Euler characteristics. That's all. So the I is telling me the homological degree in which the vector space G sub I appears, and I'm calculating the alternating sum of the G sub i's. Okay, great. Okay. Let's go on. Okay, so I'm just gonna, we can do the rest of this talk in a sort of short-term memory happy way, in the sense that if you're happy with the counting problem number 1, then let me.
Can we have another 5-10 seconds to stare at it while you talk?
Yes. Do you want me to be quiet? Let me actually, I'm gonna erase the sign computation so that I can put in 1 prime, which is the following cute observation of an equivalent way to write counting problem 1. Okay, so again, signs are not going to be important for a first encounter with this material, in my opinion. They're obviously crucial to the actual formula. All right, 1 prime. So let me remark, as you are staring at this formula, that this counting problem is equivalent to counting with the following coefficients instead. So I claim that this is another way of writing the coefficients. Namely, this thing where you have something if the graph is alternating and 0 if it's not alternating is not as natural as simply summing over all permutations, sorry, all automorphisms of the combinatorial data GM and weighing this sign with the sign of the permutation tau sub e, that's the permutation on the edge set induced by tau, divided by the number of automorphisms of G comma M. All I'm saying is that the lower expression, so the last line on this slide, is equal to the case analysis above. Do you believe that? It's the observation that you know, if G is alternating, then that actually means that all these signs in the numerator are the same. And so we have a sum of 1 over aught GM times. On the other hand, if GM is not alternating, then half of these signs are positive, half of these signs are negative, and they cancel. It's a cute observation. It's quite useful, though. Because now we're interested in counting, well, okay, let me not get ahead of myself. Is everyone cool? Can you say something in the chat if you want something to happen? Very cool, okay, great. Great. No, actually, right, okay, thanks for the comments. So the sum here is over all permutations tau, but what I'm using is the fact that if the graph GM is alternating, then all the taus act with alternating permutations on the edge set. So all these signs are +1. And therefore, I'm summing 1 over size of aught GM times the coefficient I wanted, aught GM times. Whereas if GM is not alternating, then Siddharth, I wouldn't say it's obvious, but I think it's like a group theory thing, right? And it's the alternating group is an index 2 subgroup of Sn, so it follows that exactly half of the automorphisms of GM act with negative sign. Okay, great, thank you. Okay, let's move on. So here's reduction 2. Okay, so this is going to be, I think, the conceptually most difficult. So let's try it. So look, let me go back to my example in which I had a contribution to my count. You can be fairly informal at this point, but just remember, I had a contribution to my count from the pair consisting of this sigma and this graph. So why was there a contribution? It was because sigma applied to this graph was isomorphic, again, to the marked graph. So one way to express this isomorphism is to say that it comes from an automorphism on the underlying unmarked theta graph. This is explained, quote unquote, and please just come with me on an intuitive level. That would be my best hope at this point. By the automorphism tau on the unmarked theta graph that here, let me just draw a picture of tau. Here it exchanges at these two edges. Do you know what I mean by explain? By there's an automorphism of the underlying unmarked graph that provides an explanation for why sigma acting on GM is isomorphic to GM. So here is the next combinatorial reduction. We reduce to counting pairs, I'll write G underline and tau, where G underline is so think of, I write underline for, think of it as the underlying unmarked graph. So this is an unmarked graph of genus G. And tau is an automorphism of the underlying unmarked graph. And for each such pair, so in this situation, I would have counted this theta and this automorphism of the theta that exchanges the first and the third edges. And I need to then, for each such pair, figure out how many sigmas and marked graphs GM sort of are explained, quote unquote, by that G underline comma tau. So it's like, so now the crucial point is, what is the coefficient? Like if I combine all this counting, right? So I need to count all the sigmas and all the ways to mark up the underlying unmarked graph G underline that are sort of compatible with tau, right? So what is the coefficient? And now I think I just have to ignore signs entirely. So just, I won't, yeah, I'm not going to justify the signs at all. But I claim that the coefficient is the following. And this is massive. It's sort of, okay, it's not terrible, but it's a lot of, it's sort of combinatorially, it's a lot. So let me explain what this expression means. And then I will try to just give you, if I can give you like a flash of insight as to why this is reasonable, then I'll be very happy. Let me see, there's a question. The underline G is different. Yeah, okay. So there's a question of whether I have to require stability on the underlying graph G underline. I will for the following reason. I omitted this. So, okay. Sorry, I omitted something logically. So thanks for the question. Okay, so let me postpone explaining exactly what this expression is and justify this a bit more. See, look, you know, what do these marked graphs G comma M look like? I gave you a picture of a very friendly one, which just looks like you sprinkled marked points on an underlying stable graph of genus G. In general, they could look very, very complicated. Like if you have a genus 2 graph with 1 million marked points, it almost surely has some very tricky trees of marked points coming off of it. And a theorem of, you know, myself with Galatius and Payne says that the locus, I'll call it delta GN rep of tropical curves with repeated markings, meaning non-injective marking function. So some vertex supporting at least 2 markings is contractible. Or rephrased on the level of graph complexes, it says that if you look at all the graphs for which the marking function is not injective, then the Euler characteristic of that subcomplex is 0. So that actually means that I can ignore for these purposes, and I'm sorry, I forgot that passing from problem 1 to problem 2. You can ignore all these graphs with non-trivial trees of marked points. And that's actually a huge subcomplex computationally. What you're left with then literally is marked graphs that look like M distinct marked points sprinkled onto a fixed, onto a given genus G stable graph with no marked points. And this is crucial. This is like, in some sense, it makes the whole Frobenius characteristic thing work because now we have some hope to study the behavior for all n's at once by studying just the automorphisms of genus G unmarked graphs. Okay, so this thus here is supported by point star at the bottom. Great, okay. So now I have to at least tell you, maybe briefly, what these capital P's are. So here, you know, so tau sub V, tau sub E, and tau sub H denote the permutations on the vertex set, the edge set, and the half edge set, respectively, induced by tau. And given a permutation, So given any permutation rho of cycle type A1 through up through AS, I'll just write P of rho to be the product of these inhomogeneous power sum symmetric functions. So that's what that means. Okay. So let me give you a hint as to why an expression like this could conceivably be true. This is going to be, I think, the most challenging thing for me to explain. So feel free to just keep demanding that I do it better, / we can, you know, I'll just do my best with it. So look, here's where we are. So like, I start with an unmarked genus G graph, sorry, genus 2 graph, G underline, and an automorphism of it, say the one that exchanging the top and bottom edges. And now I have to like reverse engineer. In some sense, I have to engineer the fibers of the reduction of counts that I'm affecting, right? In other words, I have to figure out which marking functions, which ways to sprinkle marked points onto this unmarked graph G, together with which permutations arise, quote unquote, are explained by G underline tau. That's really what I'm trying to count, right? I'm trying to sort of count the fibers of a certain counting problem. So you can kind of see, I mean, really what I'm interested in is the cycle type of sigma, right? Because of the way characters work. And you can kind of see that the cycle types are constrained by the combinatorics of tau. So for example, you see, like if I had any hope of reconstructing some markings and a sigma, then I had better put, for example, the same number of marked points on the top and bottom edge, maybe K. And then I have some number of marked points on the middle edge, maybe L. That number could be, is unrelated to K. And then I either have a marked point on the left vertex or not, and a marked point on the right vertex or not. Remember, again, my marking function is required to be injective due to reduction star on the previous slide. So I'm literally just trying to sprinkle marked points on, at the moment they're not labeled 1 through n, they're just unlabeled, but in such a way that they could be labeled in a way that is compatible with G underline comma tau. So you see now the cycle types are constrained. So the cycle type of this sort of arbitrary one that I've drawn here, the cycle type of such sigma is, well, in this particular example, it's, you know, let's see, I have length 2 cycles, exactly K of them. And then I have L fixed points. And then I have, you know, either 0 or 1 or 2 additional fixed points for the vertices. And this is supposed to be summed over all K and L. So I actually claim to you that the exact expression is this P tau V, P tau E over P tau H. In this example, it's a little hard to see, but note that you know what, okay. I don't know if I can explain this in a way that's, here. Okay, so in this example, this is exactly P tau V over P tau E. This happens exactly when tau never flips an edge upon when it permutes the edges. And in this particular example, this is you know, exactly 1 plus P1 times 1 plus P1 over 1 plus P1 is 1 plus P2. This is this expression. And so you can kind of, I don't know if you can see this, so let me just write it out for you. So it's 1 plus P1 squared times 1 minus P2 plus P2 squared minus P2 cubed, and so on. Yeah? So now just try to square in your, you know, at least intuitively, this expression with this one. This expression, again, forget about signs for the moment. It's supposed to be a generating function for all of these cycle types. Can you kind of see it? Because you have some 0, 1, or 2 fixed points here, and then you have this expression here. Oh, sorry, I think my calculation is off. You can at least see the 2 cycles here in this infinite series. Sorry, yeah. Okay, let me not, I think the calculation's off, sorry. Oh, yeah, okay. That's true. But now I am a bit confused. Okay, sorry, I think I have a calculational error, but I can't, I think I'd better move on instead of worrying about it. This was supposed to show the way in which this can act as a generating function for all cycle types of sigma that are compatible with the pair G comma tau. Okay, great. So there are there are a bunch of further reductions, and they're really, I wish I had more time to discuss them. The next one is so great, and I don't have time for it. So let me just explain to you in words. Now we have graphs together with automorphisms.
Sorry, just a reminder, what was tau h was the question?
Yeah, it's the induced permutation on half edges. Yeah. Okay, yeah, sorry, but there's a calculational error. Sorry about that. So it turns out then that instead of computing pairs G, counting pairs G comma tau, it's very interesting to count, it's helpful to count quotient orbigraphs, G modulo tau. So in other words, consider G quotiented by its action with tau, but now not in the category of graphs, but in a certain category of what we call orbigraphs. These are graphs together with some stabilizer data. And that was an idea that's inspired by Gorski and is quite cool combinatorics, but I don't have time to tell you about orbigraphs. So I will postpone that, and you can look in the notes. Okay, here's the last thing I want to do. So now I want to like stop with the hand waving, especially, I'm sorry, the calculational error, and come back to stuff that will appear in the homework. Because you see, I've, I was hoping to do a series of reductions accounting problems. So far, I just did one or two, I think. But you can already get the sense that these reductions can be, they aren't exactly reductions in the sense of counting over sets, but they're reductions in the sense of counting over groupoids. Because roughly speaking, things are being counted, weighed in a way that takes automorphisms into account. And it turned out, as we were writing this paper, that it was quite useful to formulate these reductions in counting problems in terms of so-called orbisummation over groupoids. So that's what I want to end with. So I'm sorry, I think I'm going to go like 5 minutes over. You're free to not come with me, but I'd like to say some of this stuff. So let's isolate the combinatorics of counting with groupoids. Okay, so a groupoid G is a category in which all morphisms are isomorphisms. And we'll say that it's finite if it's equivalent to a finite category, one with finitely many morphisms. And we'll write pi naught of G for the set of isomorphism classes in this setting. Okay, so example, consider the groupoid D sub n. Its objects are all regular n-gons of side length 1. This is a groupoid with one isomorphism class. It looks like this. And any two objects, P and Q, have the property that they're exactly 2n morphisms from P to Q. Okay, so let G be a finite groupoid. And let V be any rational vector space. And you'll lose nothing whatsoever if you just take V to be equal to Q. I mean, you'll lose nothing in terms of intuition, in terms of understanding this. And suppose F is a function from the isomorphism classes of G to V. There's any function. Then we'll define the orbis sum of F over G. I'll write it as the integral of F over G. And by definition, it's the sum over all isomorphism classes of G of not the value of F, but the value of F at that isomorphism class weighted by the number of automorphisms. Yeah, and this makes sense because we're in a rational vector space. So this is some element of V. Is it okay? A special case of this is the groupoid cardinality. So let me define the groupoid cardinality of G is the orbis sum of 1. Okay. Let's do an example. So let's consider our friendly groupoid of regular n-gons of side length 1. So then that groupoid has a single isomorphism class. And the groupoid cardinality is exactly 1 over 2n, right? So to be funny, we say that there is exactly 1 over 2n regular n-gons of side length 1. It's the groupoid cardinality of dn. Good so far? Any questions? Okay, so let's see. Sorry. Okay, so here is now the orbis, the sort of notion of pushing forward along functor groupoids that we were implicitly using when we were passing from one counting problem to the next. Oh, question. Is this where? Yes, that's right. What is the groupoid cardinality? Okay, so the joke is, what's the groupoid cardinality of the groupoid of finite sets? And the answer is E. There are E finite sets. That's right. And there are more even finite sets than there are odd finite sets. You can calculate that as some function involving E as well. Yeah, that's exactly right. Yeah, but now having done this project, I'm completely convinced that in the presence of automorphisms, you should always orbit count. You should never just count. Okay, so now suppose you have a functor on finite groupoids, F from G to H. And suppose you have a function, F, on the isomorphism classes of G. Then we define the push forward F lower star of little f to be the following function on the isomorphism classes of H by the following formula. So I have to tell you what F lower star of F is. So if you feed it an isomorphism class in H, then it spits out the orbis summation of F over the comma category F over H. So let me recall the comma category, and then I'll try to give you some vague intuition about why this is something you might be interested in. So recall that the comma category, F over H. So here the objects are so they're pairs G comma phi, say, where G is an object of G. And phi is some morphism from Fg to H. Those are the objects. And the morphisms are as follows. So you have an arrow from G phi to G prime phi prime for each arrow in G from, so I'll call my arrow J, from G to G prime, with the property that you have a commuting triangle. So I write phi prime composed with f of J is equal to phi. Okay, so that's the common category. And then the main lemma, and this is the last result I want to state in this talk, is that the orbis summation of f over G is exactly the orbis summation over H of the push forward. And this has been quite convenient packaging, quite convenient way to phrase certain reductions of counts. Let me try to draw a silly picture for you. So like, here's the deal. So you have some big groupoid and you have some function. Okay, this picture is entirely fictional. So here's a groupoid G and you have some function F and you're trying to figure out the orbis summation over G of F. And it's hard, but you might be able to break the problem down by considering an appropriate functor from the groupoid G to the groupoid H. In this way, if you were to define sort of correctly the push forward, so you have some F up here, you have a push forward, F lower star of F on the downstairs groupoid H. What the push forward does is it sort of, in some sense, it sort of orbis sums over the fibers. And this lemma is expressing that you can reduce your count, your orbit count of F over G in this way. So somehow you push the function forward to H, which maybe is a simpler groupoid, and you sort of work fiber-wise. But the formula for the orbis sum over fibers is exactly this. It's the integral, it's the groupoid summation of F over the common category. Okay, so this was maybe a bit fast in terms of the definitions. There will be juicy exercises on the problem session, in the problem session tomorrow. Okay, any questions?